Okay, so we're going to really quickly review the idea of angular quantities. This is section 8.1 of the Giancoli textbook, pages 209 to 215. First we need to talk about the things that we're going to measure in the rotational kinematics unit. So we're going to measure angular displacement, theta, we're going to measure angular velocity. We use omega for that. And we're going to measure angular acceleration. And we use alpha for that. So we just want to review how we find each one of these and what they actually mean. So when we're talking about rotational motion, we're considering rigid bodies, and a rigid body is an object in which all of the different points are in fixed positions relative to one another. So when I spin this thing, it's not going to deform or change its shape in any way. So for example, if we choose the center of the circle as our axis of rotation, and we pick some point on the outer edge of this object, another point on it, another point that's inward along the same radius would stay at the same fixed relative position to that point on the outer edge as the object rotates around. So when we talk about displacement in general, or distance, we talk about a straight line distance. If we talk about angular displacements of travel, what we need to do to consider the angular displacement, we're talking about rotating through a certain number of degrees or radians. So I can draw a line here and I can call this my initial angular position, right? Theta naught. And I can choose a new angular position. It could be anywhere around the circle, any kind of rotated frame. So here I'm going to choose this as my second angular position, theta. And we could say that the change in angular position is this, right? It's the number of degrees or radians that we need to traverse to get from this angular position to that angular position. And that's simply what angular displacement is. It's a number of degrees that you rotate through. Now in rotational kinematics we usually do this in radians rather than degrees, because all of our rotational kinematics equations work with radians. Angular velocity is simply the rate at which the angular displacement changes. The more quickly I spin around, the more quickly I go through more degrees of rotation. Angular acceleration is the rate at which angular velocity changes. So as I speed up my spin, as the object spins faster and faster and faster, each point will undergo an angular acceleration because we're subtending more and more angles every second. Okay, so how does this relate to tangential or translational velocity or acceleration? So I wrote some equations over here so that we can do some examples and show how these things relate and do some calculations. So first we need to be good at translating degrees of rotation into radians and back and forth. So we just have our conversion that 2 pi radians is equal to 360 degrees, or we could just simply say pi radians is equal to 180 degrees. So anytime we have a measurement in degrees, we can just quickly calculate it in radians. So for example, 30 degrees is equal to 2 pi over 360, or pi over 6 radians. Okay. Simple conversion. All right. So how and why would we possibly use this equation? So say we have an object that's rotating, or a wheel or a disc or something, and we choose a position on the outer edge, and we want to know how far it travels along the edge, right? What is this distance along the edge to here? Well, if I know the radius of the circle, r, and I know how many degrees I rotated through, this equation tells me how to calculate the length of this arc. And vice versa. If I know how far the arc is, and I know the radius of the circle, I can determine how many degrees I had to rotate through in order to travel through that arc. Simple relationship. Now the reason that this works is because the L has to be in meters, the radius is in meters, and the angle is in radians. Okay. Now a radian is simply a way to measure a path around a circle, with the understanding that there are 2 pi radians in one complete rotation. So if I took the radius of this circle and wrapped it around the outside of the circle, it would go around 2 pi times. So it's simply just a ratio of the length of the radius to the circumference of the circle. What if I wanted to know how quickly this point goes from here to here? Well, I could look at the angular velocity there. Right? The angular velocity tells me how quickly theta changes with time. So something interesting about the angular velocity is that all of the points in the circle have to have the same angular velocity. And if we think about that, let me redraw this circle. Okay, so we have our circle. And if I pick a point and I draw the tangential velocity, or the linear velocity at that point, if it's going around in this direction, I have to draw a tangent to the circle, like this, velocity. Okay. Now I'm going to pick several points along the radius from the center to there, here and here. Now if this object is traveling around at a constant speed, then each of these points is traveling with a different tangential velocity. Right? Smaller and smaller. Because if the speed is constant, then each point has to make it around in the same amount of time. So the inner points are going through smaller circles in order to get around to, for one complete revolution. So the linear velocities as we go inward are changing. However, if we look at the angular velocities, right, if I look at the amount of time it takes for this point to go through this angle, and the amount of time it takes for this point to go through this angle, and the amount of time it takes for that point to go through that angle, they all have to be exactly the same. So the angular velocity is the same for every point in the circle, even though the linear velocities are different. Similarly with the angular acceleration. The angular acceleration of each point needs to be constant, because it's this line of points that are speeding up as they go around. Now, how does the angular velocity relate to the tangential velocity? Well, if we can agree that the velocity is distance over time, and the distance from one point on the circle to another point is L, then that's equal to L over T. But we see from this equation that L can also be expressed as theta times r. So theta times r over t. Well, theta over t is just another way to say angular velocity. So v is equal to the radius times the angular velocity. So without having to worry too much about the derivation, from now on we can just simply use this equation. How about the angular acceleration? How does that relate to the tangential acceleration? Well, the tangential acceleration is equal to the change in velocity over time, and the change in velocity over time is r omega over t. Well, omega over t is simply the angular acceleration. So we can now say r alpha. So So the tangential acceleration is r alpha. Now here's a catch. When we're going around a circle, we have to remember that when something is spinning, it will always undergo centripetal acceleration. In order for the object to be moving in a circle, there has to be centripetal force, and therefore there must be centripetal acceleration. So this point is undergoing centripetal acceleration. Now if this also speeding up, then there will also be some tangential acceleration. And this tangential acceleration is directly related to the angular acceleration. Now if we have both a centripetal acceleration and a tangential acceleration, then there will be some resultant acceleration that I can find by looking at the resultant of these two vectors. And this, for all intents and purposes, is our introduction to angular quantities. This is what they are and how they're related to each other. Once we have these angular formulas, we can go ahead and talk about section 8.2, in which we introduce kinematics equations for uniformly accelerated motion. And those will include further equations that we can use to solve problems involving rotational kinematics.